So, next we will be looking how into an example of how to use this particular table for doing a parsing operation. So, let us consider an input string which is given by this expression. So, this A then sorry A then comma then A comma A comma then A comma A then two close parentheses. So, this is the string. So, we will see whether we can derive this string using parse this string using this operator precedence parsing table. So, as you know that we will have two parts in our formulation. The first part will be the input and the stack. So, initially input is this whole string. So, this is A comma within bracket A comma A comma A comma A and it is terminated by dollar and the top of the stack is also dollar. So, we have got open parenthesis and dollar. So, top of the stack is dollar. So, dollar is less than open parenthesis. So, it will tell that I have to shift this open parenthesis into the stack. So, the configuration changes to something like this. Then open parenthesis and dollar and then this next input symbol is A and top of the stack is open parenthesis. So, open parenthesis is less than A, open parenthesis is less than A. So, this will also be shifted into the stack. So, this input now becomes comma A comma A comma A comma A dollar and this becomes A open bracket dollar. Now, by this rule, so comma and A. So, comma, so top of the stack is A and A is of higher precedence than comma. So, A will be popped out from the stack. Now, last top of the stack is now open parenthesis and A is that symbol popped out. So, open parenthesis is of lower precedence than this one, open parenthesis is lower precedence than this sim A. So, the popping process stops. So, it is at this situation. Now, we have got comma and open parenthesis and comma is of lower precedence than open parenthesis. So, it will be shifted. So, you will be the input string will be like this. So, it will be comma open parenthesis dollar. Now, we have got this open parenthesis. So, comma and open parenthesis, then comma is of lower precedence than open parenthesis. So, it will be shifted. So, the input will be like this. So, open parenthesis will be shifted, then comma, then another open parenthesis and dollar. So, this will be the situation. Now, open parenthesis and A. So, open parenthesis and A, open parenthesis is of lower precedence than A. So, A will also be shifted. So, the situation will become so A will be shifted. So, A open parenthesis comma open parenthesis dollar. So, that is the stack. Now, between A and comma, A is of higher precedence than comma. So, A is popped out. Now, top of the stack is open parenthesis and open parenthesis is of lower precedence than A. So, the popping process stops. Now, you have got the situation now we have got the situation where comma is the next input symbol and open parenthesis is the top of the stack and this open parenthesis is of lower precedence than comma. So, comma will be shifted. So, we have got this situation, comma is shifted. Fine. Next, I have got comma and A, and comma is of lower precedence than A. So, A will be shifted, A will be shifted. Okay. Now, I have got A and close parenthesis. So, A and close parenthesis, A is of higher precedence than close parenthesis. So, A is popped out from the stack. Now, comma and A. So, comma and A, comma is of lower precedence than A. So, this pop process stops. Now, I have got this close parenthesis and comma. So, close parenthesis is of higher precedence, comma and close parenthesis. So, comma is of higher precedence than close parenthesis. So, comma will be taken out from the stack, and now I have got open parenthesis and comma. So, open parenthesis is of lower precedence than comma. So, the popping process stops. Now, I have got this close parenthesis and open parenthesis. So, close parenthesis is of higher precedence than open parenthesis, open parenthesis and closed parenthesis. So, open parenthesis and closed parenthesis, they are of equal precedence. So, they are it will be pushed into the stack. So, this becomes comma A, then this dollar. Now, I have got this open close parenthesis, open parenthesis, comma, open parenthesis, dollar onto the stack. Now, top of the stack contains close parenthesis and the next input symbol is comma. So, close parenthesis, comma, higher precedence. So, this is popped out. Now, top of the stack contains open parenthesis and last symbol popped out is close parenthesis. So, open parenthesis is of equal precedence as close parenthesis. So, this is also popped out. Now, top of the stack contains comma and symbol popped out is closed parenthesis. So, comma is of higher precedence than closed parenthesis. So, this comma will also be popped out. This comma is also popped out. Now, you have got this plus and dollar. So, now this this open parenthesis, this open parenthesis and comma. So, open parenthesis and comma. So, open parenthesis of lower precedence than comma. So, the process stops. So, we have got the next situation as open parenthesis and comma. So, open parenthesis and comma said it should be less than. So, it will go to A comma A, then dollar, then this should be comma, open parenthesis, dollar. So, it will proceed like this. Okay. So, this way you can continue in this table. So, ultimately you will find that the top of the stack input will also be at dollar and top of the stack will also be dollar. In that case, it will be in an accept state. So, you can just continue few more steps to get the final table. Next, we will be looking into the LR parsing process, which is even a better version than operator precedence, because operator precedence parsing, the basic difficulty that we had is that it cannot give us for parser for many of the grammars which do not have this operator grammar structure. Okay. So, this LR parser, so this is the most prevalent type of bottom up parser, and LRK is mostly, so in general we will call LRK. So, where k is the number of symbols that we do a look ahead. So, this LR, so this L and R, so these two letters, L stands for this left to right scan, L stands for left to right scan, and then this R stands for rightmost derivation in the reverse, rightmost derivation in reverse. So, it is in reverse because it is a bottom up approach. So, that is why it is in reverse. So, it produces rightmost derivation, unlike that LL, so which was producing a leftmost derivation. So, this will give a rightmost derivation. Both LL and LR they will do a left to right scan, but the which symbol to be replaced, so that will differ. So, we in general we will have got LRK parser. So, where k is the number of tokens that you do a look ahead or number of symbols that you look ahead. Now, in general we will have k value less or equal 1. So, we will be looking into LR 0 and LR 1 grammars. So, we will be looking into LR 0 and LR 1 grammars. So, LR 0 will give us the SLR parsing table, whereas this LR 1 will give us canonical LR type of structure. Now, why should we go for this LR parser? Because most of the parsers that you will find, so they will be of this nature, they will be LR parser. So, why should we have this? So, first of all, this is a table driven parsing. So, it is there is no recursion involved in it, and can be constructed to recognize almost all programming language constructs. So, here though it is written here as all, but it is it need not be all. So, it is almost all. So, and it is most general non backtracking shift reduce parsing method. So, there is no backtracking involved. So, you do this coding for this is pretty easy, and there is it follows the shift reduce parsing policy, that is fine. So, it can detect a syntactic error as soon as it is possible to do so. So, this is the fastest method to detect syntactical errors. Main reason is that it is following a bottom up approach, and it is trying to identify the handles in the stack. So, that is why as soon as it finds that there is a possible handle, but it cannot be derived from any of the inputs any of the sentential forms, in that case it can flash the error. So, this way it can find out syntactic errors as fast as possible, and this is the most important observation, that the class of grammars for which we can construct LR parsers are the superset of those for which we can construct LL parsers. So, if for a language you can construct LL parser, so you can also construct LR parser for that, but the reverse may not be true. So, you may be having only the you may not be able to formulate LL parser if you have got for language that can support you getting LR parser. So, there are three different methods of this LR parsing that we will be discussing in this course. One is the SLR parsing or simple LR. They are easy to implement and it is less powerful. So, powerful in the sense that the class of languages for which you can construct a parser without any shift reduce conflict or reduce conflict. So, without any conflict. So, the set of languages for which you can construct a parser. So, if that set is pretty large, we will say that the parsing strategy is powerful. If it is not that, so we will say it is less powerful. Then we have got canonical LR, it is the most general and powerful. So, this is the I should say the most general. So, for whatever language you can construct a shift reduce parser. So, you can do a you can construct a canonical LR parser for that. However, the difficulty is it is tedious. So, you will see that there are large number of states that will be created in the parser. So, that way it is difficult to make a LR CLR or canonical LR parser like that, and costly to implement, because since the number of states are more. So, you will have this policy of the program that will be used for getting this parser will be difficult. So, contains much more number of states compared to the SLR parser. So, when we look into some example, it will be more clear. Then another class of parser which is known as LALR, which is look ahead LR. So, it will do some look ahead and try to see whether it can do better in terms of resolving the shift reduce conflicts. It is a mix of SLR and canonical LR, can be implemented efficiently, and most importantly it contains same number of states as simple LR for a grammar. So, it has got same number of states as your SLR parser, but power wise it is same as the canonical LR parser. So, what we normally do is that we construct the canonical LR parser, and from there by doing some equivalency analysis. So, we try to merge the states and come reduce that canonical LR parser to a SLR to an LALR parser, and the resulting LALR parser will have same number of states as the SLR parser. However, it will be much more powerful than the SLR parser, and its power will be same as that of the canonical LR parser. So, that is why most of the automated tools that we have, so they will try to construct an LALR parser, though the construction process is difficult. So, if you are trying by hand using a pen and pencil pencil and paper type of approach, so doing it by hand, then you can most of the time. So, you will find that you can make the SLR parser by hand, but doing the canonical LR or the LALR parser by hand is a very tedious job. So, excepting for very simple grammars, so you will not be able to do it by hand. So, all these LR parsers, so we have got a concept of state, and a state represent a set of items. So, what is an item that we will define? An LR 0 item. So, when I say LR 0, that means it does not do any look ahead. So, it just looks into the current input symbol, and based on the state in which the parser is and the next current input symbol, it will take a decision like what to do. So, which state to go next, or what should be the action. As we know that there are 4 actions: shift, reduce, accept and error. So, which action to be taken. So, it will be deciding on that. So, if there is a production A producing x y z, so like this, then we can have, so all these are items. So, an item, as you can say that it is like a production rule with a dot somewhere on the right hand side. So, here, so this is an item where dot is at the beginning, this is an item where dot is after the x symbol. So, this is after the y symbol, and this is after the z symbol. So, that is the notation, but what do we really mean by that? So, when we say that we are in a state that has got this as an item. Okay. So, we are in a state where we have got this A producing dot say a dot x y z as an item. That means, in this state I am expecting to see a string which is derivable from x y z on the next input. So, whatever be the next input symbol, say A. So, that means, if I am currently in this state and the next input symbol is A, then it will be leading to derive a string. So, from this point I will expect that I will find a string which is derivable from x y z. So, this way it will try to do a prediction, like it will try to figure out which rule which type of derivation I am going to see, and that is what it will be doing. Now, what about this one? So, y producing x dot y z. So, this means we have already seen a part of the string, we have already seen a substring which is derivable from x. So, as if this is the next, if this is the input, then we are at this point A, then this part in this region I have already seen a string which is derivable from x, and then the next input symbol is A, and from this point I am expecting to see a string which is derivable from y z. Okay. So, that way, so this dot is very important. So, dot means the portion before dot is I have already seen that. So, in some state, so if I have got say a number of items like say A producing x dot y z, or say B producing say p q dot r, like that. So, if I have got say 2 items, that means I could have I have arrived to this state either by either of these 2 cases, like I have seen a string which is derivable from x, and now I am expecting to see a string which is derivable from y z, or I have seen a string which is derivable from p q, and now I am expecting to see a string which is derivable from r. So, this way, so all the items that you have in a state, so that they will tell us that they will give us enough hint about the type of string that we have seen so far, and the type of string that we are going to we are expecting next to see. So, based on that we have to take a decision, like at this point. So, if the next input is such that, so this one survives, so x producing y z survives. So, we will be going to another state where it will be advancing input, and it will expect some string that way. On the other hand, if the next input is such that, so this alternative survives. Okay. So, this is not, in that case it will be coming to a state where it will be doing like this. Now, if the parser cannot take any decision, like then of course, there will be an error. So, so shift reduce conflict or reduce reduce conflict can occur. So, we will see that as we proceed through these slides. So, this is the meaning of A producing x dot y z, and that is we have already seen a string derivable from x, and then we are expecting to see a string which is derivable from y z. Now, how do we construct this LR0 items? Okay. So, canonical LR0 items, item sets. So, it is not items, so item sets, because each of them, each of these thing like A producing dot something. So, that is an item, as we have seen in the last slide. So, all of these are items. So, all of these are items. So, when we say a set of items, so this is basically a collection of items that we had, like A producing x dot y z, so B producing p dot q r. So, these are all, so the individually they are item. So, this collection of items, so that is called set of items, and that will constitute a state. So, we see that so how to construct this LR0 item sets. So, first thing that we have to do is to augment the grammar by another rule S dash producing S. Okay. So, why do we do this thing? So, previously we had a grammar that started with S, and all these rules were there. So, in the ultimate production or the parse tree that is produced, so at the root we had got S, and then from here everything is derived. So, this is at the lowest level. So, we have got all the terminal symbols. So, what we are doing? So, we are adding another rule S dash producing S. So, why do we do this? We do this because when the parser will try to do this reduction S to S dash, then we know that we have seen the we have been successfully parsed the whole string. So, that is the idea of adding this extra production S dash producing S into this grammar set G and call it an augmented grammar. So, we augment the grammar G by adding the rule S dash producing S. Then we construct the closure of item sets. So, if I is a set of items, closure I is a set of items constructed from I by these rules. So, add every item of I to closure of I, and if A producing alpha dot B beta is in closure of I and B producing gamma is a production, then add B producing dot gamma to the closure of I. So, this is how we will be doing the closure. So, suppose we have got a grammar like this E dash producing. So, this is that augmented ETF grammar. So, we have got this original grammar had these three rules E, T and F, and we have added another rule E dash producing E as the extra rule. Now, say I 0, that is item set 0. So, this is this was having the only one rule I E dash producing dot E. So, this is for the whole this is for the situation where I have not yet seen anything. So, I am expecting to see a string which is derivable from E. So, E dash producing dot E. So, when I take closure of this, so by applying this rule, so you see we have got E dash producing dot E. So, if you compare with this, then alpha is epsilon, then B is E, B is equal to E, and beta is also epsilon. So, comparing with this, now it says that whatever we have, so B producing gamma. So, B producing gamma. So, this rule this rule survives. So, E producing E plus T, and so if I do that, then it says that B producing dot gamma should be added to closure of I. So, E producing dot E plus T should be added to the set. So, E producing dot E plus T is added. then this E producing T, this also survives by the B producing gamma as per this rule. So, E producing dot T is also added. Now, as soon as E producing dot T is there, okay, then again, so this rule has to apply. So, here alpha equal to epsilon, B equal to T and gamma equal to epsilon, and then sorry beta equal to epsilon, and then it says that B producing dot gamma. So, T producing dot T star F and T producing dot F. So, these two are added to the set, and as soon as this F T producing dot F is added. So, based on that, this F producing dot within bracket E and F producing dot I D. So, they are also added to the set. So, this way I can compute the closure of this particular set E dash producing dot E, and that will constitute one set of items. So, I 0 is the initial state of the parser, where it starts with E dash producing dot E and takes the closure of that particular item to get the whole all the items in that set. So, in this way, so we can construct the items. The another part of is to construct the go to. So, go to I x. So, this is defined for an item I, So, on some grammar symbol x, we can define a go to. So, if I is an item set and x is a grammar symbol, is a closure of all the items A producing A x dot beta, where A producing alpha dot x beta is in I. So, it is basically is A producing alpha dot x beta is in the item. So, from this if I get x, then what we are planning to do. So, that is the thing. So, if you get an x, naturally you will be coming to a state where A producing alpha x dot beta will be an item, because if you have seen x, then you will be expecting to see a string which is derivable from beta. So, this will be calling go to I x. So, the go to, so this is the set I, this is x. So, go to I x is this set, and you take the closure of this. So, to get all the items in this state, so you have to take the closure of that one. So, this is an example, like say this I 0 is the state which is I 0 is the state where which is E dash producing dot E and the closure of that. So, this is the set of items that we have. Now, from here on E, so from this rule you see the E dash producing dot E. So, if you see E, then you will be going to an item E dash producing E dot. So, E dash producing E dot. So, that is one possibility, and from this item if you get an E, you will come to a configuration E producing E dot plus T. Okay. So, that is the thing. No other rule has got a dot before E. So, they will not be coming in the set I 1. So, now in the set I 1 you see after dot there is no non terminal. So, naturally I do nothing will be added even if I take closure of I 1. So, I 1 remains this set only. What about I 2? So, I 2 is on T. So, on T if we on T if we go, so similarly we will get so this should not be E dash, this should be E. This should not be E dash, this should be E. So, E producing T dot, and from this rule I will get T producing T dot star F, and again the same thing that we do not have any non terminal after dot. So, the closure does not have anything, only these two items survive, and then I can say on. So, any other symbol like this open parenthesis is there. So, F producing dot E. So, on open parenthesis, so it will come to a configuration where F producing open parenthesis dot E close parenthesis. So, this is the item, and since now you have got a dot before this E. So, you have to again scan the grammar rules to see what may be the situations. So, as you know that the grammar had this production rule E producing E plus T. So, this has got dot E. So, I have to add this E producing dot E plus T in the closure set, then E producing dot T in this set, and as soon as E producing dot T is there. So, T producing dot T star F will be there, T producing dot F will be there, F producing dot within bracket E will be there, and a producing dot ID will be there. So, this way you can construct the set I 4. Okay. So, this way for all this from a particular state. So, you can define your go tos and on different terminal and non terminal, and accordingly you can derive new states that the parser can go.